In earlier lectures, we have seen the solution of Hermite differential equation, Hermite polynomials, and particularly the properties of Hermite polynomials like orthogonality of Hermite polynomials, Redigrew's formula for Hermite polynomials. Now, after these discussions, we are in a stage when we will discuss the recurrence relations followed by Hermite polynomials of order n, that is Hn of x. So in this regard, I have already mentioned the 4 recurrence relations for Hn of x, and you can see these recurrence relations here. First of all, we will prove all these recurrence relations one by one in a particular sequence. So I have rewritten the first recurrence relation. You can see here. This is Hn prime of x equal to 2n Hn minus 1 of x, and this is when n is greater or equal to 1. And from this result you can also see that the first order derivative of Hn of x when n is 0, that is h0 prime of x, will be equal to 0. So when you say Hn prime of x, it means this is in fact dHn of x by dx, that is the first order derivative of Hn of x. So let us now prove this. You can see this can be easily proved by starting with the generating function expression for Hn of x. And you have seen that the generating function for Hn of x is defined in this way. This is summation n 0 to infinity Hn of x t raised to the power n over n factorial equal to e raised to the power 2tx minus t square. You know, this is the generating function expression for Hn of x. Now we simply differentiate this equation 1 with respect to x. When you say we are differentiating with respect to x, you must keep t as a constant. So what will be our result? You can see that this will be summation n 0 to infinity, and first order derivative of Hn of x we can write, this is Hn prime of x and times t raised to the power n over n factorial. And in RHS, the function is e raised to the power 2tx minus t square, and when this will be differentiated with respect to x, what will be the result? You can see this will be simply 2t e raised to the power 2tx minus t square. Now, from this equation 1, which is the generating function expression for Hn of x, you can again write for e raised to the power 2tx minus t square equal to summation n 0 to infinity Hn of x t raised to the power n over n factorial. This has been obtained by the use of this equation 1, you can see. Now we can rewrite this expression in this way. LHS remains at ease, and in RHS you can multiply this t to t raised to the power n. So this will be t raised to the power n plus 1, and so we will get this equation 2, as you can see. Now first of all, we want to find what will be h0 prime of x. For this we will take simply n equal to 0 and then equate the coefficient of t raised to the power n in both sides for n equal to 0. So you can easily see when we will take n equal to 0 in LHS, there will be h prime 0 of x t raised to the power 0 over factorial 0. But in RHS, there will be t raised to the power 1 because n is now taken 0. So it means in RHS there is no term containing t raised to the power 0. So that in this condition you can say that the coefficient of t raised to the power 0 in RHS is 0, so Hn prime of x, which will be now H0 prime of x, that will be simply equal to 0. So you can see, if we take n equal to 0, then equating the coefficient of t raised to the power n in both sides of the above equation. You can see in LHS there will be simply H0 prime of x t raised to the power 0 over 0 factorial, and in RHS there will be 2 t raised to the power 1 over 0 factorial and H0 of x. So you can see in LHS there is t raised to the power 0, it means n which I have taken 0, but in RHS there is no term containing t raised to the power 0. So what does it mean? It means that when we will equate the coefficient of t raised to the power 0 in LHS and in RHS, then in LHS it is H0 prime of x, but since no such term is present in RHS, so in the RHS the coefficient of t raised to the power 0 will be simply equal to 0. So this is the result which we have also to prove, as you have seen earlier in the statement. Now again we will equate the coefficient of t raised to the power n from both sides of this equation, but when n will be greater or equal to 1. So what will be our result? You can see easily. So again equating coefficient of t raised to the power n both sides for n greater or equal to 1. This equation, what is the equation number? This is equation number 2. 2 will give. What 2 will give? You can see this will be simply Hn prime of x over n factorial, and this will be equal to, you can see here that when t should be t raised to the power n should be in RHS, but there is tn plus 1. So we must take n equal to n minus 1 in RHS to get t raised to the power n. So when we will take n minus 1 instead of n, then the coefficient of t raised to the power n in RHS will be Hn minus 1 of x over n minus 1 factorial. You can see easily. So this will be 2 Hn minus 1 of x over n minus 1 factorial. So this is the expression when actually we have equated the coefficient of t raised to the power n in both sides of equation 2 for n greater or equal to 1. And from here you can easily see that this expression may be written as hn prime of x over. You know, n factorial can be written as n times n minus 1 factorial. And so this is equal to 2h n minus 1 of x over n minus 1 factorial. So now n minus 1 factorial in LHS and RHS will cancel out, and you can see that our result will be what? This will be simply hn prime of x equal to, take the cross multiplication, this will be 2n h n minus 1 of x. And you can see this is the first recurrence relation followed by the Hermite polynomial hn of x. And from here, if you want to calculate the value of this is the result you can see here. Now we will see what is the second recurrence relation. So first of all, I am mentioning the second recurrence relation, you can see here, and then we will prove it. This is hn plus 1 of x equal to 2x hn of x minus 2n hn minus 1 of x, and this result holds when n is greater or equal to 1. And from this you will see that h1 of x will be simply equal to 2x h0 of x. So again I am writing this recurrence relation first of all, and then we will prove it. So I am rewriting it. The second recurrence relation, as you have seen, you must remember this recurrence relation to solve the numerical problem. I am writing here. So second recurrence relation is h n plus 1 of x. This equal to 2x hn of x minus 2n hn minus 1 of x, and this result holds when n is greater or equal to 1. And from here you can see that when we will take actually n equal to 0, then this result will be h1 of x equal to 2x h0 of x. h0 of x. So this is the second recurrence relation. Now I am going to prove it or derive it. You can see that this recurrence relation can be also proved simply by starting with the generating function expression for the hn of x. So we know that e raised to the power 2tx minus t square equal to summation n 0 to infinity hn of x times t raised to the power n over n factorial. You can see this is simply the generating function expression for hn of x. Now we will differentiate both sides of this equation with respect to t. When you say that we are going to differentiate it with respect to t, it means we will keep x as constant. So keeping x as constant, we are going to differentiate this expression with respect to t. So differentiating both sides of equation 1 with respect to t. It is understood that we are keeping x equal to constant. So what will be our result when we will differentiate it with respect to t, keeping x constant? You can see easily this will be simply 2x minus 2t times e raised to the power 2tx minus t square, and this is equal to summation n 0 to infinity, and here hn of x will be treated as constant, n factorial is already constant, only t raised to the power n will be differentiated, and derivative of t raised to the power n with respect to t will be simply n into t raised to the power n minus 1 and over n factorial, and hn of x will remain at h. So this is the derivative which we have taken with respect to t of expression 1. Now let us simplify a little bit this expression here. You can see in LHS the factor e raised to the power 2tx minus t square. By the use of this equation 1, we can write this in the form of summation n 0 to infinity hn of x times t raised to the power n over n factorial. So by the use of equation 1 and expanding the RHS of this equation to some extent, you can see what will be our result. You can easily see here. This will be 2x minus 2t, and from the generating function expression we can write this exponential factor as n 0 to infinity hn of x times t raised to the power n over n factorial. And in RHS you can see if we take the limit n equal to 0, then what will be our first term? You should take n equal to 0, then you can see this will be 0 times t raised to the power minus 1 or 0 minus 1 over 0 factorial h0 of x. This will be the first term. So in RHS you can write 0 times t raised to the power 0 minus 1 over 0 factorial h0 of x, and plus, now take the limit from n equal to 1 to infinity n t raised to the power n minus 1 over n factorial hn of x. Now let us simplify this expression to some extent. You can see here that in LHS we will multiply by this factor 2x to the this summation term, and then our result will be 2x times n 0 to infinity hn of x times t raised to the power n over n factorial, and now we will multiply by this 2t, so this will be minus 2 and summation n 0 to infinity hn of x times t raised to the power n plus 1 over n factorial. You can see easily that when we will multiply by t to the term t raised to the power n, that will be t raised to the power n plus 1. And in RHS you can see this first term vanishes because we have multiplied here by 0. So first term is 0, and so only the second term remains non-zero here. So this will be summation n 1 to infinity, and this is n t raised to the power n minus 1 over. Now you can see n factorial can be written as n times n minus 1 factorial, and here is hn of x. So now you can see this n in numerator and this n in denominator will cancel out, and so our result is summation n 1 to infinity t raised to the power n minus 1 over n minus 1 factorial hn of x. So you can see this is, let us say, this is our equation 2. Now you can see that what will be the coefficient of t raised to the power n in this equation 2 from both sides for n equal to 0. So you can easily see when we will take n equal to 0, let us see the result in LHS. N equal to 0, it means in first term there will be in fact 2x h0 of x t raised to the power 0 over 0 factorial, and in this second term there will be h0 of x t raised to the power 1 over 0 factorial, and in RHS there will be in fact t raised to the power 0 minus 1. But you can see when we will take here this 0 minus 1, and here will be 0 minus 1, that is minus 1, and you know that minus 1 factorial, this will be infinity. So in fact in RHS there will be in fact 0. So equating the coefficient of t to the power n for n equal to 0, we will simply get the first term, and because in RHS the term will be 0. So equating the coefficient, not 0, equating the coefficient of t raised to the power n from both sides of equation 2 for n equal to 0, we get, you can see in first term there will be 2x h0 of x, and in this in fact in the first term, in the second term there is no term containing t raised to the power 0 because there is t raised to the power n plus 1. So here there is no term containing t raised to the power 0. And in RHS you can see when we will take n equal to n plus 1, then there will be t raised to the power n, and then taking n equal to 0, we will have t raised to the power 0. So definitely in RHS we must replace n by n plus 1 to get the coefficient of t raised to the power 0. So in RHS there will be simply h1 of x, because when we will take n equal to n plus 1, then actually hn will become hn plus 1, and when we will take n equal to 0, then hn plus 1 will become h1. So this is the result which we have obtained by taking the coefficient of t raised to the power n from both sides of equation 2 when n equal to 0. Now in general, we will equate the coefficient of t raised to the power n from both sides for n greater or equal to 1. So you can again see. So again equating the coefficient of t raised to the power n from both sides for n greater or equal to 1, equation 2 gives. What it will give, you can see easily. This will be, you can see here that in first term there will be 2x hn of x over n factorial. So this is 2x hn of x over n factorial. This is in fact 2x, you can see, and this and in the second term you can see here there is t raised to the power n plus 1. So to get t raised to the power n, we must replace n by n minus 1. So in second term, the coefficient of t raised to the power n will be what? This will be 2 hn minus 1 of x over n minus 1 factorial. And now see the term in RHS. In RHS, when we want to find the value of t raised to the coefficient of t raised to the power n, but here there is the power n minus 1, so we must replace n by n plus 1 to get t raised to the power n. So what will be this? This will be simply hn plus 1 of x over n factorial. So now simplify it. You can see this is 2x hn of x and minus 2 nhn minus 1 of x, and this will be equal to hn plus 1 of x, because you know n factorial is equal to n times n minus 1 factorial. So you can use this result to simplify it, and hence you can see this is the result which actually we have to prove in this second recurrence formula. Now we are going to prove the third recurrence relation. You can see here I have already mentioned the third recurrence relation here. This is hn prime of x equal to this much. So I am again rewriting this third recurrence relation and then I will prove it. So you can see what is the third recurrence relation. The third recurrence relation actually reads that this is hn prime of x equal to 2x times hn of x minus hn plus 1 of x. This is actually the third recurrence relation regarding the Hermite polynomial of order n. Now, this result can be easily proved by simply use of recurrence relation 1 and 2, which we have already obtained. So let us write these two recurrence relation here. So you can see from recurrence relations 1 and 2 we have. You can see you have just obtained this recurrence relation. According to first recurrence relation, you can write hn prime of x equal to 2n times hn minus 1 of x. You can see hn prime of x is equal to 2n hn minus 1 of x. And according to the second recurrence relation, you can see that 2x times hn of x is equal to, not equal to, but minus, here is minus 2n hn minus 1 of x, and this is equal to hn plus 1 of x. Now you can see from this recurrence formula we can write that just interchange the LHS and RHS, and you can say this hn plus 1 of x is equal to 2x hn of x minus 2n hn minus 1 of x. Now let us say this is equation 1 and this is equation 2. Let us say. Now simply adding these two equations 1 and 2, you will get this third recurrence relation. You can see. So simply we add these two. Adding 1 and 2, we get, you can see this will be hn prime of x plus hn plus 1 of x, and this will be equal to, when we will add the RHS, you can see that this 2n hn minus 1 of x and this minus 2n hn minus 1 of x will cancel out, and so in RHS there will be simply 2x times hn of x, 2x times hn of x, and so you can say that hn prime of x is equal to 2x times hn of x minus hn plus 1 of x, and you can see this is the third recurrence relation. So you can easily prove this third recurrence relation by the use of first and second recurrence relation. So this relation is also important, but we can easily prove it by the use of first and second relation. Now we will see the last, that is fourth recurrence relation regarding hn of x. And this fourth relation is what? I am again rewriting this. This is hn double prime of x. It means this is second order derivative of hn of x, and minus 2x times hn prime of x and plus 2n hn of x. This is equal to 0. This is our fourth recurrence relation regarding the Hn of x. If you see this fourth recurrence relation, you can see this is nothing but simply the Hermite differential equation. As you know, the solution of Hermite differential equation is simply the Hermite polynomials of order n, that is Hn of x. And you know that the solution of any differential equation satisfies the differential equation itself. So if Hn of x is the solution of Hermite differential equation, this must satisfy that equation. So we know that Hn of x is a solution of Hermite differential equation. And what is Hermite differential equation? We have seen this is y double prime minus 2x y prime plus 2ny equal to 0. This is Hermite differential equation. And as we know that Hn of x is a solution of this Hermite differential equation, and since any solution of a differential equation satisfies the differential equation itself, so definitely we can write this Hermite differential equation will be satisfied by Hn of x, and therefore we can say that Hn double prime of x minus 2x Hn prime of x plus 2n Hn of x, that will be equal to 0. So this is nothing but Hermite differential equation, and so you can see this fourth recurrence relation actually says that Hermite polynomial Hn of x is a solution of Hermite differential equation, and so we can write like this. So these are the four recurrence relations regarding the Hn of x. Now in the forthcoming lecture we will use these relations to solve the important numerical problems which will be very useful for different competitive and academic examination of yours. So this is our today's lecture, and we will meet again with some new ideas, new concept in the forthcoming lecture.